welcome to the webinar that is called Towards Fair Digital Twins. This is a webinar series, so this is actually the first session, and during each session you will learn something more about the fair world and how it can help also develop digital twins. My name is Rita Gioffrida. I am working for the BioDT project, and I am involved in dissemination and communication activities for it. And I am very pleased today also to introduce you the agenda and also all the speakers that you will meet today. So the agenda is, let's say, pretty easy to read. So we will have 5 minutes of welcoming introduction, and this will be done by my colleague Sharif Islam. Sharif is the work package leader of BioDT that is linked on improving quality of data, workflows, and models through FAIR principles. And after this short introduction, you will also hear more from Ifat Zigan, Robin Richardson, and Peter Kavelka, who instead are from the Netherlands Science Center, and they will provide you a little bit more information about how FAIR principles can be practically applied also in a very practical way. I also invite you to use the Q&A chat box on Zoom. So whenever you would like to ask anything to any of our speakers, feel free to use also the Q&A. So I will now pass the floor to Sharif, and I welcome you all again to this webinar.
Thank you, Rita, and thanks again for helping us set this up. Welcome, everyone. I'm really excited that you're all here to join the webinar for the BioDT project. So BioDT is a project where our goal is to design a digital twin, and we're trying to build a system that will provide advanced models for simulation and prediction capabilities through practical use cases. However, if you look at today's agenda, we're not directly talking about digital twin. So one thing that was clear from the beginning of this project is that digital twin is not just this one big magical thing. It is a combination of data, metadata, software, workflows, and of course, best practices. And this is where FAIR principles, FAIR digital objects, and FAIR implementation come in. So regardless of the complexity of this biodiversity digital twin that we're trying to design, we still need to look at all the individual components and how these components will work together. So this idea of this webinar series is to look at these components a little bit more carefully and the different aspects of FAIR principles, and to understand how they relate to digital twins and how they can help us. So I'm really excited today that we're kicking off this webinar series with the presentation from 3 colleagues from the Netherlands Science Center about FAIR implementation. So we're hoping to learn a lot from them, from their experience, and to understand how we can think about FAIR and how we can be applied to FAIR digital twins. So today, first, we will hear from Ifat Zigan. She's the section head of environment and sustainability at the Netherlands Science Center. After which her colleagues Peter Calverla and Robin Richardson, who are both research software engineers at the Science Center, and they will provide examples of FAIR implementation from different projects. So without further ado, I hand it to Ifat.
Hi, everybody. Good afternoon. And first, I want to thank Sharif for inviting us. We are very happy to give this first webinar. And we wanted to talk about how we implement FAIR principles in our project. So how do we do that? How do we do that at the Netherlands Science Center? But before we even start, I thought it would be wise to tell you about the Science Center, what it is, who are we, and so on, because most of you probably don't know us. So just a second, yeah. So as Sharif said, I'm the section head of the Environment Stability section in the Science Center. We are the National Center for developing research software for research in all disciplines in the Netherlands. And our objective is to use digital technologies to advance science and to support societal change. And our mission is actually to empower researchers through innovative research software or through innovative technology. And we put this into practice in our 2 ambitions. So one is to collaboratively design software for research in our research projects. And the second ambition is to build digital capacity and expertise in the Dutch community. So the instrument to achieve our first ambition is our collaborative projects. So we published open calls, and these calls can be applied for by any researcher in the Netherlands. And so you as researchers can apply to work with us, and we provide the in-kind contribution, which means research software engineers that work on the project together with you. And you can come up with any scientific question that's applicable, and we try to implement the state-of-the-art digital solutions to these questions. One thing we always try to promote is open and reusable software, data and knowledge, and so also open science. Our second ambition is to build digital capacity in the scientific community, and there are different ways to do that. So we develop and teach different carpentry courses, like the one I mentioned here is the parallel programming in Python. We publish a lot of blog posts on the technologies that we develop, on the projects that we do, on the principles that we use, and we provide also tools to make your to really help scientists develop this expertise. So all the work that we do is actually done by research software engineers, which is a term that you probably never heard before. And these are experienced researchers, so most have PhDs in different domains, and that can be from high energy physics to climate research, digital history, and so on. But they also have strong affinity with technology, and that means that they are able to understand both the research question, but also the best technological solution that we can offer to and to help and solve this scientific question. And our expertise range from AI to analytics, data processing, and efficient computing. And we put a lot of emphasis on software quality, and as I said, on making our software open and fair. And we believe that open and fair software actually will help us to have an open and fair and reproducible research. So I'm the section head for the environment and sustainability section, and in this section we have around 15 engineers from that have different backgrounds, and they all work on projects from climate to earth observation, ecology, hydrology, and everything in between. And in the near future, we would like to focus on climate research, on establishing ourselves as an hub of excellence for remote sensing, so for Earth observations, from data access and storage to analysis. We also want to explore fields like geohealth, and in terms of technological focal points, we want to focus on digital twins, on developing machine learning for geosciences, which gaining more traction now, and on green computing. So one last thing that I want to mention that we have recently published 2 open calls where we ask researchers to apply for and to see if they want to collaborate with us and to work with us and to utilize our expertise. So please log in to see these open calls. And I think after you hear from Peter and Robin, you will see why you want to collaborate with us. But on top of these calls, we are also looking for other opportunities to collaborate. So please feel free to contact either me, Niels Drost, who is our program managers, or one of the engineers that you feel is applicable for you. So now I think Robin can tell you a bit more details about one of the projects.
That was a lot of pressure.
Sorry about that.
So let's see. Okay, yeah, so I'm going to start off by just talking about, can everyone see the slides?
Yes, we can.
Yeah, okay, yeah. So I'm going to start off by talking about just general FAIR principles. This is going to be fairly high level. The initial part of this talk, I'm not going to go into digital twins specifically, but I'm going to go into the idea of making scientific workflows fair in general, and some of the issues you might get when you do this from a high level, pure kind of theory approach. So first thing here is, what do we mean by scientific workflows? So I quite like this cartoon on the left here that shows essentially the way a lot of science is done, or all science. You start off with some data, you'll do some manipulation with tools, maybe process it with some code, and in the end you get results which you publish. What do people actually publish? Well, they don't necessarily publish the entire process, whereas the science is in fact the entire process. It's not just the codes which people publish more these days, or the transformations that have happened to the data that you can actually remember. People tend to write papers where they give a subset of the actual journey that data took to results. This is something that we do see, and there is a very commonly used term, the reproducibility crisis, which some of you may have heard of. And this refers to a number of studies in various fields, starting with, I think, psychology, but eventually they discovered this problem everywhere, that attempts to reproduce landmark studies ended largely in failure. This doesn't mean that the studies were wrong or false, although some of them probably were, but rather just that key information was missing in what was published, or whether in the journal itself, or whether in supplementary information or by other means, that other researchers could not reproduce that study. If you look on the right here, I think this is best typified by the top image. So what we're calling the current paradigm, although hopefully this has already changed a little bit. The idea that due to time pressure and the need to just publish, what really happens is you take data, you do whatever it is you need to do to it, analyze it, then it goes straight to publication. And at that point, that data is basically never used again, or if it's used again, it's used by the same research group. Where in fact, what we want to move to is a system where other people can check your research or validate it, or at the very least build on top of it, make new hypotheses, start from your data, from your work. Very closely connected to this is the development of what are called the FAIR principles. We can't really do this without saying what they are. FAIR stands for findable, accessible, interoperable, and reusable. These are intended as basic requirements for publishing and reusing digital resources. The basic idea behind it is that a lack of high quality metadata makes it very difficult to use data, to reuse data. If you don't know where the data comes from, that's also a big contributor to irreproducibility. And other issues like a lack of clear licensing terms, which hinders, again, the reuse of that data and therefore innovation. So FAIR is intended to some way accelerate research and discovery by actually allowing people to reuse your work or start from it, which is kind of the idea behind science, I would say, or should be. Something else that I should mention here is, and maybe it's a bit more applied, is that somewhat recently, there's been the release of the FAIR principles for research software. So this is, if you like, the original FAIR principles are talking about data in general. You can argue about whether software is a form of data. It doesn't matter. One is it's a category of data, and you can have specific FAIR principles for it. So in this, I'm just going to look at these. So in terms of findability, we're saying software and its associated metadata should be easy for both humans and machines to find. So this both humans and machines will be a key thing later. Accessibility, so software and its metadata should be retrievable via standardized protocols. Interoperability, this means that you should be using standard file formats or APIs, or at the very least that you should describe how you're doing that in some standardized way so that people can interoperate with your software. And finally, we have reusability, which is very closely connected to reproducibility, I think. The idea that the software is usable and reusable and can be understood, modified, built upon, incorporated into other software. This is a large part software licensing. There's a little link at the bottom for anyone who wants to go look at these FAIR principles for research software specifically. But we're talking about FAIR principles here for both the data and for the software. A common kind of attitude, and it was very much my attitude, or even still is to some extent, is that you look at these FAIR principles and you look at the detail of what's been said, and the impression you get is really, okay, we use some kind of standard protocols, we publish all of our data, we publish the input files for our simulation code, etc. and we just give everything a DOI when we publish it. So yeah, that's fair, right? It's basically done. And yes, to some extent, that's true. In fact, if you do that, you've already done something really quite useful compared to what was happening in the past. But there's something that's a bit more tricky, I think, and it's what's called provenance. So here I've quoted from the FAIR principles. There's some sort of sub rules or clarifications of each one. So for reusability, we see here metadata are associated with detailed provenance. Okay, what does this mean? Well, so provenance is, in short, where did this data actually come from? So who generated it? What generated it? Is it combined from multiple sources? How has it been processed or transformed in the past? Who did that? You know, and ideally, where this data came from and its history should be described in a machine readable format. And this creates some trickiness as well. And I put this sentence here because I think this is what comes out a lot in when we attempt to apply FAIR at these centers. Anything with provenance, useful provenance, collecting provenance in a useful manner is a hard part of doing FAIR properly. Okay, what does provenance mean as applied to scientific workflows? Well, we have these two terms I think are in somewhat common use now. We have prospective provenance and we have retrospective provenance. Prospective provenance is essentially, what do you intend to do? What's the plan? What's the recipe that you're following, or what's the experiment that you're about to carry out? Whereas retrospective provenance is a description of what actually happened when you attempted to follow a particular plan. And that may or may not be anything like the same. These are both provenance because they're both required for understanding where your data came from. So you might think prospective provenance sounds a bit weird because it's not really what happened to the data, but it's what the intention was when people were carrying out these transformations. And therefore interpreting the data requires you to know what people were also trying to do. So I think that, at least my understanding of why you would call both of these provenance. There's this requirement that I've mentioned of the way you describe provenance needing to be formalized in some way, machine readable, following some sort of standard so that you actually know what the terms mean. So you should use some sort of controlled vocabulary, or at least. One way of doing this is not the only way of doing it, but a relatively popular way of describing this is using the resource description framework, so it's called RDF. And this is essentially describing data by defining relationships between objects. So objects here are essentially concepts. So in the form of a triple, so that's subject, predicate, object. Is what we've got here. An example of this would be if we wanted to say that Tim Berners-Lee, so the inventor of the World Wide Web, if we want to say he is a person, well, in English, you can just say he's a person, but in fact, that's hiding a potential amount of ambiguity in what does is exactly mean? What does person exactly mean? This sounds a bit ridiculous when you're talking about a person, because we all know what it means, but machines don't necessarily know what this means, right? There's a lot of context there. So you use RDF with usually URIs that point to what these concepts actually mean. So there's a specific concept for Tim Berners-Lee. There's a specific predicate that defines what is means, so what type is, and then there's a specific concept of what a person is. In this case, it's in this friend of a friend ontology. And once you have a number of these different triples, you can build a graph. That's what's on the right, and essentially effectively a knowledge graph. So it contains all of the facts we know about the system. And this is machine readable. So this fits a bit what we want. How do we, what's an example of how we could use ontologies to formalize provenance? Well, here we have the P-plan ontology on the top that's showing prospective provenance. So here we see that we've got concepts of a plan, concepts of steps that belong to that plan, variables that are being used for these steps as inputs. And then on the bottom, we have the prov ontology. So this is concepts relating to having applied steps of this plan, having applied the whole plan. So what actually happened when you did it? The reality of this, if you want to apply this to a real general scientific workflow, is something a lot more complex. So here I put this sort of diagram that I don't even think this is complex actually compared to what you might need to develop, but it looks pretty, well, pretty frightening at least. This one was an attempt to basically describe a scientific workflow, including manual steps, computational steps, everything. And it's not just randomly chosen, it's in fact a project we worked on here. This is called the Fair Is as Fair Does project. We were working with the Maastricht University and the VU. And this was a very kind of, I don't want to call it theoretical because we attempted to apply it, but it's very much, you know, describing entire workflows using semantic technology. So, and in that way to render them fair. So what did we actually do? Well, no sane person, no sane researcher is ever going to basically willingly write out all of that RDF to describe what it is they're doing or what happened. You pretty much have to automate this. So in this project, we attempted to help this method become real through a number of different tools. So one is the Fair Workflows Python library that aids in automatically generating prospective and retrospective provenance. So through the addition of Python decorators to code, I'm going to show another slide on that. And then a place to publish that. Here we've used a nano publication network. I don't want to go into what that is, but it's basically just a place you can send your RDF to, so little bundles of RDF. So what does this actually look like if we apply this to, say, script? So this is a kind of a toy example. So let's say we have a step from a workflow. So this is Python code. We focused on Python. It's very commonly used language in science, but in principle, we want this to apply to all manner of workflows. So here we have an add step. It takes X and Y and returns a float, right? The decorator is this fair step decorator that we stick onto the front of that function. And if you do that on the right of the, you'll see the RDF, so the provenance, if you like, in RDF form that was generated by that decorator. So it's been able to generate prospective provenance of that step and what that step intends to do. So this is actually a very brief sort of code, but it actually generates a lot more provenance in this. And on the bottom, we also see the workflow decorator. So in this case, the workflow just has a single step. It runs that add function, and then it returns the value. And on the right, again, we see the prospective provenance that's generated for that plan. What I've not shown here is that when you actually execute this code, it will also generate retrospective provenance for everything that's happening. So this is an attempt to recreate the very complex model we saw on the previous slide, and generate a big graph, a big knowledge graph of all of the facts about what we wanted to do and what actually happened. Now, what do you actually do with that provenance when you get it? Well, I'm going to switch to basically my final slide from this bit. Is the lessons that really came out of doing all of this work. The first one I think is obvious, and I don't need to convince you of it. The automation is important. I think this goes beyond doing it in this quite high-level semantic technology way. No matter how you collect the provenance, most users will not collect it or will forget to collect certain key bits of information. So there needs to be automation. The second part is useful provenance is really hard. Again, this doesn't have to be to do with the RDF I'm discussing. You can log everything you do. You can just, publish all of the logs of your simulation code running and all of the files. That doesn't mean that people can necessarily do anything useful with it later. In principle, it contains all information needed to understand what happened, but that's not necessarily what people can do. Thirdly, I would say that purity comes at a cost. I think purity could perhaps be translated as idealism. So here, In this case, the ideal system is one where you capture absolutely everything in a formal machine readable way. But in fact, this actually makes it very difficult to ask questions of what you've generated at the end. You've generated a huge amount of provenance, you've got a massive graph, but actually writing the queries or thinking of the questions you even want to ask of this is surprisingly difficult. So you should try to think what it is you really want to get from it and what you want people to do with the provenance, and limit the data model complexity wherever possible. My final point is that I think it's important to remember that it is the spirit behind the rules of FAIR that actually matters. It's very tempting to treat it as a kind of box-ticking exercise, to just read through the rules and just apply and make sure you've done all of these things. But if in doing so, you actually create a system which is extremely difficult to reproduce, if you create data that's very hard to use or use it to understand where the data came from, then I don't think you've not really made it fair, right? So I think that's quite an important point. Yeah, so that's the end of my slides.
All right, then I will take over. Just want to quickly check whether the video is coming across clearly.
Yes, as of now, everything is clear.
Okay, perfect. Then I will continue with the part about the water cycle. This is much more a pragmatic story, I think, than what Robin just showed, and I think it's nice to see that contrast as well. So e-water cycle is a project that we did over the past couple of years, in which we try to make a platform for hydrological model, and we focused a lot on doing that also in a fair and open and reproducible way. So the story starts in 2019. April 2019, there was a workshop organized together with the Lawrence Center, and at this workshop, several hydrologists and research software engineers came together, and they wanted to discuss the problem of reproducibility in hydrological modeling studies, because these studies had grown so complex that it was hard to reproduce them, it was hard to compare them among each other. It was hard to exchange parts of models or perhaps even input data sets or outputs. So that was a problem. And at this workshop, I think it was a key moment where people came together and decided, okay, this needs to change and we want to do it differently. And at that point, we did have the FAIR principles, but they were mostly targeted at data management. But the idea, of course, as Lawrence already mentioned, also extends to other parts of the scientific endeavor. So we thought it would be nice to see how we could apply that to hydrological modeling. So a very quick overview of how of the overall challenge in hydrological modeling studies. It usually looks roughly like this. So you start with a couple of input parameter sets. Typically, we split them into forcing data and parameter sets. So forcing data is weather data, precipitation, sunshine, temperature, etc. And parameter sets are static files. So, for example, the land use, soil type, those kind of things. And if you have both of these, then you can try to use a model, feed them into a model, and the model describes how the water that falls over a certain area collects through the landscape into rivers and then flows downstream towards the sea. And in the end of the study, you typically, well, what you often make is one of these figures, a hydrograph, where you plot the discharge of the river over time. So that is a very basic overview of what a single hydrological model does. Now, during that workshop, basically everybody brought their own model, right? And you can see that the type of structure of the modeling study is still very similar, but there are different choices. So you see the models themselves are different. They're a bit rough around the edges, but also they made different choices in the input data sets that they used. For example, different forcing data or different parameter sets, and that results in different outcomes. And you can see the silo structure here, right? So this actually, it is very difficult to exchange models, to use one another's model, to compare outputs from different models, etc. And this was a challenge that we wanted to address in the water cycle. So this is all the Lawrence workshop. Now I'm going to go through the story of how we try to solve this problem. I'm going to start with the chapter of fair models. So what we wanted to do was to see, well, perhaps there is some kind of fair standard that we could use to make those models more interoperable, easier to reuse, more alike, basically, without actually touching too much how the models work under the hood. And we found that it was actually a very good standard. This was called the Basic Model Interface. It was developed in CSDMS in the US. And there they realized that, well, the models themselves may be implemented in different languages. They may work very differently under the hood, but there are some similarities as well. For example, they all have a time loop. They all use input data. They all produce output data. So perhaps if we can just standardize that interface, then it already becomes much more interoperable. And then, of course, with software, it's also a challenge you have to download the source code of a model, you have to compile it, etc. Setting that up can also be a pain, but we also knew that, well, there were things like container technologies. So we thought, well, if we use that as well, that makes it even easier for people to use and exchange each other's models. So in this case, we found, well, that's really cool. There is a sort of fair standard. The only downside was that it was not used much. But okay, we were early on in the project, we were ambitious. We wanted to change the way that people did their hydrological modeling studies. So we decided, okay, let's be a leader and just start using these standards and hope we can influence others. So we did. We wrapped all these models with a basic model interface, packaged them in a Docker container, and then wrote a small Python package from which we could control these models. That was part one. Then we wanted to address the forcing data. So remember, the forcing was the temperature, precipitation, time-dependent data. And in this case, we started again and looking whether there was a fair standard. And in this case, the answer was, well, there is something, but it doesn't quite fit. And the something that there was climate data. There have been, of course, all these IPCC reports, and every cycle is supported by a so-called CMIP study, which is a model intercomparison study. And in order to compare all these different climate models, there have been really, really good standards. They're called the CMAR standards, and they define a controlled vocabulary for variable names, etc. And then there was also this software that we had used before. It was called ESM-Vol tools, Earth System Model Evaluation Tool. And this tool actually leverages these standards in order to make it easier to load data from different climate models without having to know exactly the locations of the files on disks, for example. So that's a really nice example of where the usefulness of fair data comes in and standardization. And ESM-Vol tool is a software to then work with the climate data, analyze it, produce some sort of output. So this was a really good standard, and we would love to use it, but it didn't really accommodate all the different types of input data sets that we wanted to use. But luckily, there was a way to make it work, because ESM-Vol tool, and I think this is a very smart approach, it's a sort of pluggable software where you can add new data sets. And what you do then is you write a small summarizer script that basically transforms your input data to adhere to the same standards as all the climate data. And once you've done that, you can easily use it. And then also at the other end of the tool, you can write specific user-defined functions or recipes, as ESM-Vol tool calls them, to well, make some small modifications depending on what your model requires in terms of input data. So we found that really useful, and we found out that we could make this work for our use case. So at this point, I think the important lesson here is, well, even if there is not a perfect standard yet, sometimes you just have to try and make it work and start using it. So I think this is an important lesson. Pragmatism beats purity in this case. So that's what we did. Next chapter, the parameter sets. So this is a very, very different journey, because we found that there was really nothing like a standard that we could use for dealing with parameter sets. So I'm going to walk you through what happens next. Well, you can think, can we set it? We were not the owners of the parameter sets. The parameter sets were very different. So we didn't really feel that we could do that. And also we had already lost a lot of time on the models and the forcing data set. So, okay, that was not a possibility at that stage. So then the next question is, okay, perhaps we could make it feel like there is, and that will become clear in a minute, because if you don't think you can, the next step to do is, well, can you develop a wishful example? If there would have been a standard, what do you want it to look like? How would I want to use it? And I think thinking about it in that way is really helpful. Now imagine you can't even think about what you would want to do with it, then perhaps you should wonder, do you really need this fair standard? And if you still are convinced that you do, then you should probably raise an issue somewhere in an appropriate place. But in our case, we found that we could think of a wishful example. It could look something like this, for example, in some wishful thinking Python code. And well, once we thought, okay, well, if it looked like this, well, perhaps we can even make that work. So we found that by thinking about a wishful example, we could actually make at least that part work. And it's far from a fair standard yet, but at least it's a minimal convention that we thought we could embrace and introduce, and then we'll start using it and see what people thought, and maybe we can improve on it. And I still think it's important that we could raise the issue somewhere, but at least now we have something to show, like, okay, there is not a standard currently. We think this would be helpful. What do you think? All right. So now we tackled most of the challenges related to the intro slide I showed before, but we also made a platform. And well, going back to what I showed before, we started with this. Now we have something like this. So we have an in-between layer that sort of ensures that's basically a compatibility layer that makes it possible to use different forcing data sets, different parameter sets, and control different models from a uniform interface. And this was a Python package, but you would still need to pull all the Docker images, install the Python package, download all the data sets, etc. This can still be easier. And of course, people wanted to make hydrographs, so we added functionality for that as well. And then we wrapped everything into a platform. So we set up a machine with the models and the data set already prepared, the analysis environment configured. And I think even though this is not part of the official fair standards, if you will, it does help a lot with the accessibility and definability, interoperability of whatever you're doing. And also by giving people access to a platform and showing them like, okay, this is a really convenient way to work. I think you can show the benefits of making things interoperable, and then hopefully they will start to embrace it. Especially even if you grow bigger and you say, okay, this is the way everybody does hydrological modeling now, then anybody that has their own hydrological model would like to add it to our platform. And then we can say, well, go ahead, you can do it, but you need to adhere to these fair standards. So I think having such a platform in place is really nice. And we use Jupyter Hub as a main backend for also user authentication and so on. So that's nice. We even added a graphical layer, which I will not go into detail, but this makes it even more accessible by making it possible to set up an experiment basically with visual tools instead of in programming. And then it will generate in the backend a new Python notebook in which you can start an experiment with everything already set up for you. So I'm going to summarize here. This is an overview of our FAIR expedition. And this is basically showing a historical path that we walked. And I don't think this is an all-encompassing chart that will apply in your case or in any case. But I do think there are some important lessons here. So, for example, it is really good to show off the benefits once you started doing something fair. It's also important to well, as a big project, to show leadership and to say, okay, this is how we think it should be done. So just do it and start doing it. And then when you encounter that something is, in theory, it would be really nice and perfect, as Robin just explained, often in practice, it's a bit more harsh. And sometimes you just need to well, bend the rules to whatever works for you. And then finally, I want to stress this wishful example. We have found it really useful to think in that way about, okay, imagine there is a fair standard, how would we like it to look like? So these are some of the main messages from eWaterCycle. I would love to go more into detail, but I don't have the time right now, so I'm going to end here and open the floor for discussion, I guess.
Yeah, thank you. This was really exciting, and I'm really glad also that you highlighted the sort of the spirit of FAIR and being pragmatic and practical. I think that's also a lesson we're learning as we're thinking about it. So yeah, the floor is open for questions. We have time. I will mention a few comments already. So yeah, there's a comment that the FAIR for software principle explicitly say that software is not the same as data. Maybe can you quickly mention like why does it matter if it's not same or if it's same? Is that?
I don't think it matters. I think it's more that how you apply the principles. It makes sense to take account of what category of the data that is. If you feel like it's a kind of philosophical question, if you like, but of course software is data. Like just about anything is data if you choose to think of it that way. I think software has some. Software is a specific type of data. And therefore you can be more specific in the rules of how you would make that fair. I think it's about helping people make it fair. So if you can develop general principles for all data, but then if you know something more about what kind of data it is, like in this case it's software, then I think you can be more specific in the rules, and that helps people understand how that applies to that category of data. If that makes sense. Yes.
One example could be maybe a quick example, like for example, how do we handle data versioning versus software versioning?
Yes,
there's some similarities, but still software versioning and data versioning has some big differences. Yeah,
I think so. There's a huge amount of overlap. Of course, these are ultimately the same principles, but maybe with clarifications for what they mean for software. Yeah.
Okay. And then there was a question on the chat about the prospective and the retrospective provenance. I'll just quickly read it. Could you explain how prospective provenance actually work in the example? Addition was actually literal in the triple. Is this parse to achieve a receipt of required computation steps to reach a previous state?
Yes. Yeah. So this is a bit the kind of like the theory, like ideal theory versus practice part. So what you actually perceive as what real prospective provenance will be for people doing this pragmatically is the actual code they ran, the actual workflow they followed. In this particular project, because we were following this, let's make it all super formalized, super machine readable, and so on, we decided to describe all workflows, whether they're computational or manual, using the same set of triples. Yes, part of the project was, can you then read that in and then execute this description? And that was very much the goal of the project. I think we got some way towards being able to do that. So reading in the prospective provenance and being able to execute it, reconstitute the code. The problem is kind of it's very fragile, this kind of way of doing things. Describing everything in these triples, in principle, you can describe everything, but in practice, these triple stores or these graphs are a bit fragile in how you interpret them, and recreating executable code from its RDF description is very non-trivial. So I think in terms of pragmatism, you could view prospective provenance more as being, for you guys, it'll be whatever way you describe your workflow in code, and then with a little bit of RDF description in there, rather than trying to bundle the whole thing in. If that makes sense.
Yeah, no, thank you. That's good. And I was also curious. Did you had any performance issue with RDF handling?
Yes.
Large set of RDF and how?
Yes, it's very slow. So again, it's kind of it's a technological issue you get when you attempt to describe things in this way. It's extremely powerful, but querying these graphs, so you can make Sparkle queries, which is basically like SQL queries for this kind of graph database of triples. Constructing these queries is actually non-trivial when the graph becomes very complicated. They're also quite slow, at least in my experience, quite slow to return, and that's I think because there are not very many optimizations you can make when you're keeping this level of complexity. I think that kind of, and this isn't really my area, but I think with the kind of knowledge graphs that people use these days, you can limit that complexity a bit and have faster, more optimized queries. But yes, it's in principle, it's very slow, I think. Yeah. Although we may have been doing something wrong, but I think it's yeah.
So one thing within the digital twin use case we have to handle is combining sort of static snapshots data with kind of like a real-time data or data streams in different use cases. I was wondering in the hydrology project if you had any experience sort of combining the snapshots with sort of real time, and how did you, are those data formats that you mentioned, can they handle those things in that level, or?
Well, the basic model interface that we used allows for communication with the model in the container. So in principle, you could stream the state of the model through this gRPC channel that I showed to the client. But we have no specific use case that would use this. So we haven't made any more specific applications at the client side that would leverage this. But in principle, the technology allows it. Yes.
Okay, yeah, and that also brings me the question of the container and Docker in general. So are there any, I mean, in a way, your Docker container has to be also fair in certain way. In a way, you can handle it as another digital object. Because oftentimes I do see, Docker files are not running. They're missing components, missing libraries, or not updated. If you had any way to solve some of those issues.
Yeah, it's a very good question. What to say about this?
I mean, I think it's probably clear that there's advantages of the containers because you can package things in, but maybe I don't know. Yeah, please go ahead. Yeah.
Well, so indeed. It is a challenge, and we also found that we set some of these Docker containers up somewhere in the beginning of the project, and then later on we had trouble even finding back the source files, for example, the Docker files that we used to create them. So it's a very good point that in order to use these as other fair digital objects, you would have to. So of course we do have Docker Hub, although that has, well, things have been going on around Docker Hub that also perhaps you should question whether you want to rely on that service, but at least it's a place where you can host and exchange container images, and they provide room for metadata to some extent. They also provide automated builds and so on, so that could help to check on basically the health of the container images. But I think, well, in that respect, there is still room for improvement also in ways of exchanging containers. Maybe also relying on, so one thing we also did in the water cycle was rely on Singularity instead of Docker, because that also often works better on high performance systems because you didn't need root permissions or something like that. And Singularity is now changing to Apptainer, but well, at least, well, perhaps it has a slightly different way of handling the images as well. So perhaps there is developments there that might also be interesting to have a look at. I don't have a conclusive answer on how to make those containers entirely fair, but it's a very good point that, well, this is something to think about.
Yeah, and there are also some comments in the chat about around reproducibility. Yeah, maybe you can also look at that. Okay, there's another question about machine actionability and machine readable format. So it seems that it's a key aspect of FAIR principles, but the question asks, I'm not entirely sure what that entails. What is and what is not a machine readable format? So let's say I'm working on a project that uses a certain set of data, software, and workflows. How can I make sure that all the elements check this machine actionability box of the FAIR principles?
Yeah, that's a bit of a hard question. I mean, these days with AI, I suppose the machines can read just about anything, can they? But I think it refers. My understanding was that machine readable refers to having set a clear standard for what the terms are. So it's more to do with being able to that the description you're using is itself described somewhere else in a very clear way. You could argue, I mean, perhaps that these concepts themselves are maybe slightly out of date in the AI era. That a machine, in order to understand things, needed logical relations between things. But I don't know if I'm not sure if machine readable has a hard and fast definition in the way that it's used in FAIR. I'm sorry, it possibly is written somewhere. I would say that I think I would just read it in plain English. That is this a format that's easy for a machine to parse? I think the FAIR principles, again, I might be wrong, but I think the FAIR principles generally don't try to force a particular use of technology. I think they just, it's just as long as you can easily enough parse this description with the machine, and then I think that you're meeting that point. Don't quote me on that.
Yeah. There was also a comment in the chat for Docker container storage. This example, they use GitLab, especially some of the reasons about Docker Hub. So yeah, I think that's also an option, another option. And also you can assign DOIs to those Git repositories, so probably can add other metadata.
Yeah, I suppose you can publish Docker images on Zenodo or somewhere like that, which is persistent. I'm not sure what kind of file sizes you're allowed. Docker containers tend to have very large image sizes, but a huge problem with any hub that you use is that after a while they stop hosting those images. You can find the Docker file, but you can't necessarily rebuild it.
And the Docker images are also built up of many layers, right? Yeah. So it depends on them being available. So that's one of the advantages of singularity. Then you just compile the whole thing into a single file, which is the image. That is easier to just publish somewhere, I guess.
I think so. As long as you have to be careful that the compilation itself isn't pulling in packages which are hosted somewhere and that these links always die. This is kind of link routes or dependency routes problem.
Yes, yeah, I think we will run into the same problem when we get to our digital twin in the HPC part as well. Yeah. There was a comment surprised about the RDF performance. Was this in Python? As I recall.
Yes, yes, it was. It was RDF lib. Perhaps I think you can probably get much more optimized performance than we did.
Okay.
But it wasn't a critical problem with this particular project. Yeah.
Yeah. So we have only 6 minutes left. So maybe another question I'll throw out to whoever one of you can answer. So one thing we are also thinking about within digital twin projects is to, of course, we have the research infrastructure involved, but we also have data sources coming from different places. And sometimes, within the research infrastructure community, we have control, but some of the other data sources, we cannot really, sort of dictate the fairness or quality. So I was wondering if you have any sort of opportunities or methods to communicate with the wider community where the data is coming from. Like, how do you do you organize workshops, or how do you provide the feedback that, okay, like the data I'm getting from your community is not fair, please do, X, Y, and Z, or what, yeah, I was curious that if you can provide some.
Well, I think sometimes it's hard to influence other parties or data providers or model developers or whatsoever. But on the other hand, it can also go the other way, right? So if everybody from a user community embraces the standards and embraces the tools that are able to work with fair data, that in itself creates an incentive for data providers to make sure that they also provide their data in the standard. Otherwise, people will not use it, or will have a much harder time using it. So, and indeed, the workshop aspect is another one, right? So if you really think this is a problem because you have many data providers and they all do something different, for example, that was, I think, one of the strengths that we had this Lawrence workshop early on in the e-water cycle project, where different parties sat together and they together agreed, like, okay, we're all going to make an effort to try and standardize here. So I think indeed a workshop could be a really good option in some of these cases. And I can really recommend the Lawrence Center because they collaborate in a really nice way to organize very professional workshops.
I think it's quite.
And they're close to you in Leiden, I think.
Yeah, they're here. But great.
I think it's quite important for these standards that people feel ownership of them. I think initially you get this problem with everyone growing their own sort of homegrown standards that they would really like everyone else to use, because then it's kind of like a political thing as well as a technological one, or it's largely political. So organizing workshops is a good way of doing it, because you can potentially publish a white paper or something. And I know this sounds like just generating more papers for no reason, but I think that actually does work. People feel like they have some ownership of this and there's something they can cite and they can develop it. They're more likely to use it. They feel like they were consulted as well. Whereas if you just find out there's one other group that's using standards, I don't know if that always convinces people to jump. Ideally they would, of course. I think in practice and science, it doesn't necessarily work like that.
So yeah, I think we're coming to the end of the hour. Yeah, there's also a lot of conversation going on in the chat about workflows and things. Maybe you can look at it. But yeah, I think we need to close the session. Thank you so much to all the speakers. And I really enjoyed it. And I think one of the main thing I want to emphasize is to understand again that it's a stepwise process. I really like the flow chart where you kind of follow different aspects, sort of the spirit of FAIR and the pragmatism, and also at the end we talked about this idea of community building and ownership. I think these are all things I think we're also thinking about within Digital Twin, and really exciting to see this example. So thank you so much once again, and thanks again for everyone to join. And just a reminder, we will have another session. Some of the similar things we'll talk about in detail. We invited Dr. Daniel Katz next time in our webinar session to specifically talk about the FAIR for research software. So hope to see you again in a few weeks. Check our website. I think the recordings will be up there, and we also have other information about the Digital Twin project. And hope to see you guys again, and probably other collaborations. Yeah. Thank you.
Thank you.
Thank you.
Okay,